Okay, so we are at the very crucial place of the course. It is called the fundamental theorem of calculus because it is really brings things together. I have been hinting at this statement certainly many times. In fact, on the very first day of classes, I brought it up, and that's how the problem of the how obviously related the problem of finding the velocity from location to the velocity of finding location from velocity. Okay, so they obviously related, and then what remains is just to interpret these two problems, they opposite of each other, relate to the problem to the problem of on one hand the tangent problem. Okay, tangent problem, finding the tangent line to a curve on one hand, and on the other hand the area problem, how to find the area under the graph. So what do they have to do with each other? When they stated entirely a separate way, whatever they have in common is only, well, we're dealing with a function, there's only one function, and ultimately the question is there, both of these issues are with the limits. But the limits are actually secondary, as we saw this week, when the relation between the slopes on one hand and areas are entirely related. Okay, so let me show you that as a reminder one more time of what we did. No, wait a minute. It was what was it? Picture. Here it is. Fundamental theorem. Okay, so ignore the velocity business, but if you look at the first graph, then you can think of it as well. Let's look at it. What are the slopes? I'm sorry. What is the area? Okay, so the areas, those areas are, as we progress from left to right, the area grows, and then we plot the area on the right. Okay, so that's one kind of problem. And then the problem, that seemingly unrelated problem, suppose we'll have a bunch of points plotted, and then the question is, what are the slopes? And we plot the slopes on the right. Okay, so these are two seemingly unrelated problems, slopes on one hand, areas on the other hand. And so let me make that point with some kind of a big. So one problem. And this one might appear entirely different problem. Okay, so once again, this one is from dots to slopes. Okay, and we just plot the slopes. On the other hand, over here, from graph to the areas. Okay, so areas and slopes turns out to be very clearly related. As you can see, we started with that graph over there. We plotted the areas. Then we took those areas and plotted their slopes. Okay, and what the end result is the same as the beginning. That's the same exact graph. So the fundamental relation is in fact clearly visible when we're just dealing with nothing but numbers without limits. It is a challenge now to actually restate the same for actual slopes of tangent lines rather than those secant lines, and for areas that are as curved as this. Okay, so let's do that nonetheless. So as you can see, the main step we already have made, and that is to construct the area function. Okay, the area function as we move from A to the right with the origin changes. So we are moving like this. As t goes towards b, as for any function it would, the area changes, and therefore the number, the origin changes. So origin grows, and region's area also grows, even though, well, it grows when the function is positive. Okay, so when it's negative, then it will be declining. Okay, so but let's say it is just what picture shows. The function will be growing. Okay, so and then the conclusion in that is the fundamental theorem, right here. Fundamental theorem of calculus, is that the derivative of that function will be the original function. Okay, so once again, the area function of y equal f of x, so some kind of function we start with. So at least it has to be integrable, but generally we might require more than that. So it might, let's say, continuous. Then this would be over here. Okay, and then this is the statement of the fundamental theorem. Before I stated one more time in full glory, so to say, let's see why it is true. I hope it was clear why it is true, or maybe it wasn't entirely clear why it worked out this way it did. It seems that it's such a simple steps that we have taken here, and then it produced the same result. Just rearranging those bars. That's all there is. But this one is way more complicated because there are infinitely many slices of infinitely thin width over there in order to understand the area. So let's just look at it and try to differentiate. So I'm looking at the right-hand side of the area function. So this is the area function, and I'll just differentiate it, and I'm supposed to end up with f. Okay, so f prime of t is, well, it is the derivative of the function. Let me write it explicitly. F x dx, and then prime. Well, actually, probably let's go with the definition. Let's go with the definition. There is really no formula for f. We're trying to solve the whole problem right at once. All possible functions will be taken care of. So this is what the definition of the derivative is: f of t plus h minus f of t over h, the difference quotient. That's it. Okay, so now use the definition, which in the proof that happens more often than you think. And then in the next time, let's substitute. We substitute the formula for the function circled on the right. So I have the limit with h going to 0. Okay, and then in the numerator, I still have my denominator h. What do I have in the numerator? Look at the second term. The second term is simply my function. Okay, the second term, f of t. See that f of t is the same as I have circled there. So it will be integral from a to t, f of x dx. Okay, but what is the first term? What's f of t plus h? I mean, if you have the formula for f of t, how do you find the formula for f of t plus h?
Add h.
To what?
F of t.
No.
T.
To t, and not even, should think about adding h to t. You replace t with t plus h. That's all. It's substitution. It's substitution. Because what if I ask you what is f of 5? Well, f of 5 is integral from a to 5 f dx. Okay, so that's the substitution. That's the formula for whatever the formula of the function is. You just replace the independent variable with that number, what you have there, or whatever you see. So it will be integral from a to t plus h f x dx. Okay. Now this is tricky. We want to simplify it. We want to simplify it. The numerator. We are just, as every time, remember we did derivatives from the definition by the limit. We end up with 0 every time, 0 over 0 every time, and we are in the exact same place. So we have to simplify in order to complete the computation. So what do we do with the numerator? How can we simplify the numerator? A factor? No, I don't think you can factor it. I mean, yeah, maybe at some point you will be able to factor it, but not just yet. You see it? Let me plot it for you. This is A, this is T, and this is T plus H. Okay? So we incremented T to T plus H along the x-axis.
You subtract H.
From what?
T plus H? Or T?
No. No, let me show you. Let me show you this picture. So let me plot. There are two terms in the numerator, and I can plot them then over here at the same time. So the first term is this. This term is this. It goes from A. It is the, remember, the integral is the area, right? So the domain of integration is from A to T plus H. See, this is the domain from A to T plus H. On the other hand, the domain of the other one, this one, the domain is this, from A to T. Okay? So then the second integral represents this area. Okay? Then what is the meaning of the difference of these two areas? No way. So these are the two areas. Where is the difference of these two regions? So one region in green, the other one, and one is in purple. If I subtract them, what do I get?
H.
No, not H. This one is H. This one is H. Yes. But what I'm talking about is this region. Yeah?
I know it's an integral, so H is going to be on top by itself.
No, not on top. No, not exactly. Remember, there is a rule for it. It's called the additivity rule. When you add the domains, you add the integrals, and when you subtract the domains, you subtract the integrals. Okay, so in order to subtract these two integrals, all I have to do is to subtract the domains. So the numerator is one single integral. What is it? The yellow one. Still divided by H. How do we represent that yellow area as a function, as an integral? It is the area under the graph of the same function. The only thing that matters is the limits. So what are the limits? T and T plus H, right? So it looks kind of narrow because H, we can think of H as small, but really it is just another region under the graph, and it is on the left it is at T, on the right is T plus H, so it will be integral from T to T plus H. All of the same function, there is no other function. Okay? So that is the simplification that we have achieved, and at this time we should be able to figure out what this limit is if we zoom in on this picture, and this is what it's going to look like if H is small. So H small. Remember, H goes to 0. So suppose H is small, then what happens to the curve? This curve, it's almost not a curve, right? It's almost a straight line, or whether it is horizontal or vertical, that doesn't really matter. Well, you can. So then the area is still this, right? This is still H, okay? And what is this? So the width is H. this is x, this is x plus h. And what is the meaning of the height? It's like almost like an ideal bar, like this, the way we talked about when we talked about difference, when we talked about the Renaissance. So the width of the bar is h. What's the height of the bar? What's the height of the bar?
The anti-derivative?
No. No, just look at the graph. Look at the graph where it came from. This is what we're talking about. This point lies on the graph of the function f of x, right? F of x. F of t, technically. Yeah, sorry about that. This is f of t. Okay, so f of t, so the area is f of t times h, right? So that's why this expression over here is approximately equal to f of t h over h, or f of t. Okay? So that is the informal way, somewhat informal way of dealing with this, is ignoring those possible corners over there sticking out from under this bar, and replacing that area with still a curved top. We replace it with a rectangle. If we do, and those errors, look at them, they are really tiny over there as h gets smaller. Whatever happens over here, that doesn't really make any difference. So then the area of we're talking about, the numerator is what we're talking about. The numerator is this, the yellow one, okay? And it is f of t times h, the height times the width. And that allows us to cancel h and end up with f of t. The actual proof requires the mean value theorem, but this one explains. This one is really the advantage is that it actually explains why it is the way it is. Okay, so indeed it is just as the approximations improve, the slice, the difference between the two values of the function will be the area of that thin slice, and the area of the thin slice is getting closer and closer to what? To simply f of t, that area, f of t. Okay, so so that explains why we have our fundamental theorem. If this is less than convincing, then you could certainly improve the argument somewhat. Instead of looking at the bar, you instead can think about what it is, a trapezoid. Remember, we just talked about a trapezoid, which doesn't really change anything. So if it is a trapezoid, then what's the difference really? It means that this one will be f of t, and this will be f of t plus h, and the area of the trapezoid will be f of t plus h over 2, but still multiplied by h. And then you divide by h, and then what happens? The same story. You still end up with f of t. So you can improve this somewhat in that manner. So once again, the approximation by the trapezoid will be better than by the bar, but ultimately you need a careful proof that relies on Riemann sums from scratch, starting with Riemann sums for this kind of a Riemann integral, and then the mean value theorem actually comes into play and makes that happen. Okay, so all right, so that let me state the theorem. So there are two versions: fundamental theorem of calculus. Part 1, well, not part 1, it's the same part, it's just different ways of looking at it. So we have, suppose f is continuous on an integral AB. So then we define a new function, once again f capital of t equal integral from a to t ft dt, fx dx rather, fx dx, and t lies between a and b. Okay, so, well, what is f of 0? I'm sorry, what is f of a? It will be 0, right? So there are some things that you should quickly think about what's going on, but to see what's going on, and some of the things are kind of obvious, but if you just give it a minute of thought, so that is what I'm saying here is that the function certainly starts with at 0 when the t is equal to a, then it is integral from a to a, which is has 0 width, and it produces 0, and then it might be increasing or decreasing or not. So and then we say either we say f prime of t is equal to f of t, or we say that f capital is an antiderivative of f. Okay. So what is the so let's quickly review a certain topic from a while ago, and that is, what about the rest of antiderivatives? So you remember what I'm talking about? So the concern should be right here. So I say it is an antiderivative. Okay, so what about the rest? So are there other antiderivatives?
There should be.
Okay. For a different point on the graph for what? It is in a way. It's a trick. Is let's get back to that in a minute. So what do you remember about antiderivatives of the same function? What's the relation between them? Antiderivatives?
It's just backwards. It's diversifying the derivative.
Right, but there are two antiderivatives. Is there a relation between them?
They're the same.
No.
Are you talking about on the same function?
Same function, yes. So we found one antiderivative of f apparently. What about the rest? Okay, so when in doubt, what?
B to T, or say this first one is from A to B or A to T, from B to T or B to A, would that be the second one?
Say it again from...
Like this one right here,
yeah,
that we have is from A to T and A to B, but then
yeah,
taken negative from B to T or B to A.
well, no, that would be the in the negative. No, it's not an antiderivative. You reverse. I think you're talking about reversing the direction of the interval. No, that's not gonna work for another antiderivative. So when in doubt with these concepts, it is stated in the theorem that's the way it's supposed to be. But if you're in any doubt, then you can figure out what's going on. Go back to the metaphors, and the metaphors are what's the metaphor for a function and its derivative? Location and velocity, right? So then which one of these two is location and which one is the velocity?
The antiderivative is location.
That's right. So f location, and then and this one is velocity. So then the question I'm asking about, if the velocity was given, okay, and then we found one location function, one. Okay, are there any other? With the same velocity, could you have a different location function?
With the same velocity?
Yes.
It's proportional.
Not proportional, no.
Because if it was linear, right?
No, no, it's not about proportional. It's about the two persons running, well, two cars driving at exactly, they are talking on the phone and they maintaining exactly the same speed or velocity. So what is the relation between them?
Same starting point.
Well, then they would be driving side by side. What if they start different places?
Their displacement's the same.
Right, at every moment of will displacement the same, which means that the distance between them will be preserved. You can have like a rope between them; it will never break or hang. Okay, so that's the thing about velocity. So no matter how, if they change speed simultaneously, there will be no separation of them. It is as if they're the same object, just located in a different place. So mathematically, you remember what it is. So another one is, so one is F capital, another one is, the difference is a constant. Remember that plus C business? No. When you do anti-differentiation, you have plus C every time. So that plus C gives you the rest of the antiderivatives. For each C, there will be a new antiderivative. So this is how. So F was given. Okay, well, F was given somehow, maybe like this. So this is F. I'm now plotting F capital. Well, let's say this is A, and I start adding. And this is still A. So I'm starting. That one of the problems you did in previously. The derivative is known. Find the function. So I'm plotting the function, but this time I'm being more specific. And I know that f of a is equal to 0, which means that my graph is going to start right here. Okay, and then as you can see, a function is positive, so it will be going up roughly, and then still going up, but not as. And then, well, actually, I do accelerate faster in the kind of I accelerate, and then kind of I guess it kind of flattens out, maybe. If this one is kind of becomes horizontal, then my graph of my location will be, it's like I am stabilizing my speed, right, which means that I will be progressing at an almost linear fashion over here. Okay, so starting kind of slow, accelerating, and then stop accelerating and going with the same speed. Okay, so this is the area function, y equal f of x. We can think in terms of certainly we can think in terms of areas, but in terms of velocity and location, but also you can think in terms of how the area is changing. Just look at it. So this is the first one increasing, then the next one is increasing faster, and then increasing faster, and then at some point over here it's not increasing faster anymore. It is the area increasing every time by pretty much the same increment. So this one is equal to that one, and so we're adding every moment of time. We're adding roughly the same amount, which is exactly what linear function is, and so that's why I'm plotting here kind of a linear one. Okay, so that's one of them. The rest of them are right here. They differ by constant. So how do I get the rest of them from this one? Function differ by constant. What does it mean graphically?
It'd be the same graph with the same slopes, just shifted.
Shifted vertically. So either I highlight it, or well, I actually can. I think I've done this before, but it's worth repeating a few times. So if I go and highlight it, well, okay. Let me make a better picture here. 1. Okay, it goes like this and then straightens up. Okay, so if I highlight it, copy, paste, I could produce a bunch of these, right? By doing copy, paste, I am creating new ones, like this. Okay, so the same exact shape, shifted vertically. The difference, once again, is nothing but the location. And it is determined by one thing and one thing only. It is the initial, if we want to think in terms of motion again, it is the initial position that matters. So the one that we have picked, the initial position is 0. F of A is equal to 0. Okay, so that one I marked. But you can have any other one as well. So on this line, which is a straight line along the y-axis, I could pick any point. And attach that graph again and copy as many, and it will fill, these graphs will fill the plane. Okay, so without intersecting. So it's like what is it like? Well, sometimes you see like layers like this when you see maybe some kind of digging or maybe driving, and you can see how at some point it was blasted through a mountain. This road, and you can see a wall here with different layers, and they are not usually like this, they are usually like that, and they are kind of those layers of different geological periods. They follow certain curves. Well, those are not necessarily the same, but they are certainly curved, and that's roughly what should come to mind. I don't think I can well, layer cake maybe. What is it? What else is it? This one is good because a layer cake. Well, and then you take a layer cake and then you kind of shift it or twist it, so to create the this kind of pattern. Now that's all good, but once again we have to go to our metaphor. Go to metaphor literally every time. Go to motion and location versus velocity whenever you are not sure about the abstract concepts. But really, let's go back with this understanding and see what it means for our theorem. And so we're in this theorem provides us with only one antiderivative. So how do we get the rest of them? And it's really not complicated. We can simply change. That's we're going back to that idea. We can change not the initial position necessarily, but you could write it like this. So you can write simply say g of t is equal to f of t plus c, which is integral f of x dx plus c, so well from a to t. Okay, but you can also shift the alternative idea is to pick a different starting point for integration. So say I pick c here. Okay, so, well, not c, but how about d? Okay, so g of t could be seen as integral from d to x to t, f x dx. Okay, so varying the not the initial position. That's what picture on right shows, but rather varying the initial time. Okay, and so you certainly can progress to the left or to the right of that point to, and what is the difference then? How do I find f here? Well, by that picture that we already did, when you split two integrals like this. So this is say t, and this is d, and then the integral from a to t, which is this, will be equal to the integral of 1 from a to d and then from d to t. So this one is equal to integral of from a to t, fx dx. Okay. Okay, tell me what follows here. So I'm talking about g. G is this. This is g. Okay. But I want to go back to f capital, and I want to look at the integral of over the whole thing. So in other words, this one. What's the difference between them?
B a to t minus a to d.
That's right, minus integral from a to d fx dx, which is a constant. That is the meaning of that c. So this is c. It is also an integral. Just it is because the limits are fixed, so the constant is fixed. So from A to T, and so from D to from A to D, and from D to T. Okay, yeah, okay. So so that's one interpretation, and the other one is virtually it's not identical, but looks quite a bit different. But it is very very important because for actual computations, and it is the idea comes from from the actual displacement. So so if f is velocity once again, then and say f is the location. Okay, so then our actual integral f is not the value of the of necessarily. So see, I'm looking now not at a variable length, variable upper limit function that I have here. So location function, but rather I'm looking at a full displacement. This is what this is, displacement over AB. So you AB is the time you have driven, and then the integral from A to B will be your displacement. But okay, so that's a thought that we have used before. So the integral is the displacement over the velocity is the displacement over that period of time. But at the same time, it is also the displacement is also the difference of locations. That is the definition of the displacement. The final location minus the original location. So in other words, it will be f of b minus f of a. Okay, so and whatever f is, so there is that relation between the velocity and sum of the location function. Doesn't matter which. Doesn't matter which, because that what do they have in common? All of these antiderivatives, all of these location functions, they have the same displacement. Okay, so it doesn't matter which one you pick. These two functions, say f and g over there, what's the difference between them? A constant. So when you subtract f of b minus f of a, or you do g of b minus g of a, it is the same. It's naturally the same thing. So so let me state it, and then we'll apply it a couple of times. So. So fundamental theorem, version 2. It's slightly more general. We assume that f is integrable over AB. So it means simply that the Riemann integral is defined. So every continuous function is integrable, but also step functions are integrable even though not continuous. So f is its antiderivative, which simply means that f prime is equal to f lowercase. Then, and then this is the formula, and that is the most common way to represent the fundamental theorem of calculus. Okay. So so when you're stating theorem, never forget about the conditions. So it's like with the Pythagorean theorem. If you just say a squared plus b squared is equal to c squared, you are probably wrong because you didn't say what those things are. So once again, if you're stating then the fundamental theorem, you speaking of f lowercase, f uppercase, you have to say what they are. Okay. So okay. So let's apply it. Let's apply it. Well, let's do a simple one, the one that we started with. In fact, yeah, let's do the one that we started with. Remember this one. The graph is 1 minus x squared. Okay, this is the region from 0 to 1, and this is also 1. And we had to go through the Riemann sums and summation and that formula. Remember that kind of complex formula of the sum of squares consecutive integers. Okay, and now we get it for free. We get it for free because why? Because we know how to do antiderivatives. So an antiderivative is a reversal of derivatives, and we have just a few rules that we can use anytime. So so then let's first things first. We have to represent the area as a Riemann integral. So the assumption is, well, the problem is find the area. Okay, find the area under the graph of this function, and then what do you do first? Represent it as the integral. So the area is, okay, what's the integral?
0 to 1.
0 to 1. Yeah. What's the function?
That is the antiderivative of 1 minus x squared.
Well, no, not yet. That's how we're going to compute it. Right now, we're simply writing it up. So that is the write-up. So like a starting point, translating this sort of geometric problem into a calculus problem. Okay. So and then what we do is, well, let's identify things that we're looking at. So in the idea is use the fundamental theory of calculus. So how? You have to identify f lowercase and f uppercase. This is f lowercase, right? So f of x is 1 minus x squared. F uppercase is its antiderivative. So
Is that the whole thing?
no, f is antiderivative of 1 minus x squared. So if you remember how we do antiderivatives,
x3 over x.
no, what's an antiderivative of 1? You remember we split it by the sum rule. We split it. So what antiderivative of 1 is? No, that's the derivative. The derivative of x is the derivative of what? 1 is the derivative of what? Of x. X. And what about x squared? X cubed over 3. So it is the product rule of the the power formula for antiderivatives. The power goes up and divided by the formula. So let me refresh your memory. xr dx is equal to, this is indefinite integral or antiderivative, and this one is definite integral. So Riemann integral, definite integral, same thing. Okay, so and it is 1 over r plus 1 x r plus 1, okay, plus c. And so as long as r is not equal to -1, that is the formula, the power formula. And then I could add plus c here. It doesn't make any difference because we're going to subtracting it, so that plus c won't make any difference. So then the area is equal to, according to the fundamental theorem of calculus, it is equal to f of 1 minus f of 0, and that is really uncomplicated because now I just I plug in 1 into my function, so it will be 1 minus 1 cubed over 3, right? So that's f of 1, and I substitute 0 minus 0 cubed over 3, and then what? That's pretty much it. It will be 1 minus 1/3 or 2/3. The end. So that was pretty easy in comparison to that computation. So that is to be remembered that the formulas of calculus help us to a lot with the computations that otherwise would require limits. So that helped us a lot with differentiation. Remember, that was a while ago when we started with the limits, and then we are not doing limits ever again. Same with antiderivatives. It's just not as we just not unable to go as far and as easily because integration is harder. So that's why it all spills over into calculus too. But this one is pretty successful actually, and it is quite a revelation. Yeah.
Is the antiderivative of sine x negative cosine x?
Yes.
All right. So you just work backwards.
That's right. There's nothing else. This is the definition of antiderivative is the reverse of the derivative. As long as you remember plus c, you will never go wrong. But just remember that it's not always working out as easily. So the power formula is good, sine cosine is good, exponential function really easy, but anything, I mean, think about how easy to differentiate, well, that's maybe not easy, but try to differentiate this function. So what's the derivative of this function, just to see if you remember how to do it?
X squared times e minus, or to the...
No, you're forgetting to differentiate.
Would be e to the 2x.
No, 2x is outside. The chain rule is you differentiate the function on the inside and it comes in as a product. So the function on the inside is x squared, so I will have 2x over here. Derivative of the function on the inside. And the second term is the derivative of the original function, which is simply ex squared. So that you'll have to refresh and practice a bit before the final, hopefully. So that is that's the formula. And then think about it. Try to imagine that you were supposed to go that backwards. It was hard enough to go forward when you're just getting familiar with derivatives and the chain rule especially, and then now try to go backwards. That's quite hard. Certainly virtually impossible to guess unless you've done this differentiation many times. Then you'll start recognizing things. So we'll talk about that in a while, and then hopefully we'll see some of the methods of how we can handle things like that. But the idea is still that is firmly should be in your mind that the integration is a reversal of differentiation. So then they cannot stand apart from each other, which is what the fundamental theorem is all about. So you cannot find areas without understanding derivatives. So because once again, f capital prime is f lowercase. Okay. So worthwhile to do what we started with. So one more example. Remember what we started with, and that was a computation of the, let me find it, the approximation, rather, of the area of the circle. No, this one. Okay, so remember this one. So nothing but the function which gives me the height of the formula that gives me the upper half of the circle, which is, see that formula over there, to simply I'm sorry, I'm looking at the wrong place. This one. Okay, it is 1 minus x squared, square root 1 minus x squared, and then we just build the bars, not too many, 20 of them, and then multiplied by the width times the height, added them together, and the end result is here, and the 1.55355, and which is close to the actual results, which is pi over 2. Okay, so also, but that was an approximation, can be improved, but really doesn't prove anything. So if you want an absolutely accurate result, then you have to carry out this integration, and so we're not entirely prepared to do that, because but it's still worthwhile to at least to do it once to follow up that example. So I'll find the area of a circle or a semicircle. Say the radius is r, so minus r. Okay, so that's my area. So find it. So you're supposed to end up pi r squared over 2. If you only want half, I want only half only because I'm supposed to represent the function of. I'm supposed to. My area is. We can handle some areas but not others, and we can handle the areas that are area under the graph of a function. And the full circle is not the graph because, why not? The vertical line test. So the curve makes the full circle, and that's where it cannot be the graph. Fortunately, we found the way out, and that's cut it in half, relying on the symmetry of the picture. And at some point later on in calculus 2 and 3, there are ways to get around it and compute area of anything of any region on the plane. So anyway, so then the top graph is the top edge, the round edge is given by f of x equal to square root of 1 minus x squared, okay, or r squared minus x squared if I want to go with the radius. And then so then my integral is, the area is integral, what are the limits? Negative r, and this is my function, r squared minus x squared dx. Okay, so that is, the setup is done. Then we can, at this point, we can forget all about the geometry and just do the calculus problem entirely. And certainly this is a fundamental theorem of calculus. So so in order to solve this fundamental theorem of calculus, we have to we need to find antiderivative of this function, r squared minus x squared, and with our experience that we have had with finding antiderivative, we really do not know what this is. So we, most of the time, we just remembered that at some point we differentiated this function, so we know the answer, and that answer is now taken backwards, and we know where it came from, so that's the answer. Okay, so we, at no point we ended up we differentiated anything and end up with this formula. So, well, the answer is really not. So what is antiderivative of this? And we cannot really handle it from scratch, certainly, and in order to find antiderivative of this function. So until calculus 2, fortunately there is a book, and in the end of the book there's a list of integrals. For that particular occasion, if you don't remember the answer or cannot find it quickly and you need it, then that's what you do. So the formula is quite, the answer is quite intimidating. So I'm just copying it. Okay. So arc sign appears. Not only we have that square root again, but also we have the arc sign. So this is taken from a table of integrals. So table of integrals in the end of every calculus textbook, okay, inside the cover, remember. Also, sometimes they're listed inside that section on the integration. So just when the lists are short. And if in old times you had like books like this, literally this thick, filled with integrals. Okay, so the scientists or engineers could look up and just integrate it. Nowadays you can probably go to Google, type that function in, and it gives you the answer. Or if not, go to Wolfram Alpha. You know what it is? Yeah. So they will integrate. They will give you the formula very quickly. So then you realize that that computational part is really, best we can hope ever to learn it is now being done by computers. So it is that part that precedes it actually is the actual what we're trying to learn. How to understand limits, how to understand tangents, slopes, how to understand areas. And so that conversion that we reach this point, this point over here, that is the human thing, okay? Then to figure out and to set it up. And then once it's done, the computer will do a lot of it for you. So also don't forget that the numerical part that we started with, actually, that's also, nobody will figure out the formula of the region that you're trying to find, the area of which you're trying to find. And so that is also cannot, the computational part, once again, easy, is done by the computer. But it is up to you, once again, to command the computer. So just to wrap it up, let's substitute and just see that it works out as we expect. So it will be integral from. So we take this formula and plug in. Well, let me repeat the formula. So this is just notation is also matters, a matter of presentation. I dropped the C because I don't care, and this is the notation. X runs between negative R and R. Okay, so that vertical bar indicating that we're not going to end up with a function, but rather with a number, and here we will be plugging in two values. And the top one will be plugged in first, and then the second will be subtracted. Okay, so if I plug in R, I have R over 2, and here I already have things start to disappear, right? That will be 0. R squared over 2, arc sine of R over R. That's also simple. Okay, so that's the first term. And the second term I plug in negative R, which doesn't really make any difference for the first term because it will be still R squared minus R squared, so that will be gone. And here I have R squared over 2, and I have arc sine, but this time of negative R over R. Okay, so I finished the substitution. Now, once again, this is gone, this is gone. Okay, so now R squared over 2 is here. What's arc sine of 1 minus arc sine of negative 1? Okay, so that's where trigonometry comes into play. So what's arc sine? What are arc sine of 1?
Over sine equals 1. Is it 0 or 1?
No. So the question is, what is x? The sine of which is 1. What is the angle that gives you sine equal to 1?
Is it pi over 2?
Pi over 2, right. So always like this. So this is the sine. This is pi over 2, and the sine will be 1. Okay. What about negative 1?
3 pi over 2.
What?
3 pi over 2. Or negative pi over 2.
No, yeah, that's right. So a negative pi over 2. It does make a difference, right? Because the function is only defined on the for these values of x. So it's negative pi over 2. So the end result is r squared. So it will be pi r squared over 2 pi. Yeah. Okay, which is the correct answer. Okay, so that works out. I had this afternoon. I had in my calculus 3 class. We pretty much run through a similar example. Only we were computing the volume of a sphere. So 4/3 pi r cubed. Well, so not really that you don't really get that far. So once again, it's one formula next to this formula. Are they really that much more complicated? Not really. It is the stuff about functions and how they work, and then you have vectors and you have multiple variables. That's what makes it hard. This computation is really not a big deal. Unfortunately, this becomes a big deal because it's like every test you take of calculus, you will be facing a problem like this, because it's so easy to ask to solve it, and then easy to verify whether you're right or not. So it's like asking in an English composition, ask you to spell things. So, well, if you can't spell, you probably are not good at it to begin with. But on the other hand, then it doesn't matter whether you can write good essays or poetry, and you only test it for spelling. So this is spelling, pretty much. Okay, so I guess I'll stop here. So once again, don't forget the